Hi everyone, and welcome to another restoration at Mr. Carlson's lab. Let's get started. Let's test and verify the operation of this professional dwell tack. Now, much of the times these things are sitting under the hood of a car and they're vibrating, so they're usually out of alignment, and much of the time they really didn't come from the factory aligned very well anyways. The stuff is just so quickly moved down the line. So we can kind of tweak this thing up and maybe make it as close as possible. Now keep in mind with all of these, and this is something that you need to keep in mind whenever you're working on any of these older devices, an issue is scale linearity. Now I've seen this so much, and I expect this thing to have this as well. With the everyday standard professional dwell tack, you got to remember that you're taking a signal in here, and then of course you're converting that to an analog movement on a scale. So unless you're really dealing with a device that's, the engineers have spent a lot of time, and there's usually some form of scale, linearity issue. So we'll see if this one has it, and if so, we'll talk about it at that point. All right, so what I'll do is I'll get a function generator set up, obviously because I don't have a V8 and a 4-cylinder and a 6-cylinder on my bench here. It'd be kind of heavy, right? So I'll show you how to align one of these things with a function generator. It's really simple, and I'll share all the math with you as well. You'll find that if you look for math and a proper description of this kind of stuff online, it's kind of tough to find. That's just the way it is, right? So what I'll do is I'll break it all down to a very simple and very easy explanation, and you can write this down on a piece of paper or whatever and save it for the future if you ever want to take one of these things and align it yourself. And that'll also go for the dwell. The dwell is a little bit more complex, but I'll share all that math with you as well. So let's get going. I'll get the function generator set up, and we'll have a function generator at the top of the screen here for us to look at. Let's verify or test the 8-cylinder high RPM range first. So that's the upper scale on the meter here, and that's just above the yellow line here. So 30 is 3,000 RPM, and just below the line is the number 6, which is 600 RPM. So that would be the 8-cylinder low RPM setting. It's always a good idea to test it at center scale first. The very first thing that you need to do before you really try to do any sort of alignment or any type of verification on a meter like this is you need to make sure that the mechanical movement is zeroed. Now there's a bunch of tricks with this. I kind of have to get the center screen because it kind of shadows. You can actually see the shadow here. So in order to adjust this right onto the zero mark, you can see this is very well zeroed. You just put a screwdriver in this little adjustment here, like so, and you can see if I twist this, can bring it off of 0 or below 0. So we want that right on the 0, right about there. After you've done that, what you want to do is take the meter and rock the meter back and forth like this and see if it still sits on the 0, which it does. You'll find that if you do that and the needle moves up and stays there, or moves below the 0 and stays there, you know that you have sticky movement inside the meter. And that has to be fixed before any type of electrical alignment or any type of verification can be done, because the needle can move and then jam up, or it can add extra resistance to the movement in the meter, and that'll cause, of course, accuracy issues, right? A lot of the times what happens over time with these meters, especially with the older dwell and tack meters, is the plastic shrinks and it tightens up on the internal movement of the meter. So if it tightens up on that movement, of course, you're going to get a sticky needle. Now, there are ways to rectify that problem. You can kind of see through this hazy area. There's a little adjustment screw under the front cover. Sometimes, depending on the meter you have, there'll be an adjustment screw on the back that you can get to, and that has to be loosened off just a touch. And there's a bit of a science behind that, and I'll share that with you in another video on how to actually repair the movement of these meters. So once that's done and this is sitting on the 0 mark and everything is good, usually you're good to start your verification process at that point. So I'll move this back under here. So now, in order to do this alignment on your bench, you need a thing called a function generator. Now, that's not to be confused with a signal generator. There are two different devices. A function generator will provide you with a square wave output, and you can also adjust the duty cycle of that square wave. Now, there may be some devices nowadays that will, perform both functions, a signal generator and a function generator, but it's most commonly two separate devices. Okay. The math for this is really quite simple. All right. So in order to adjust or verify the 8-cylinder to do the alignment. This is the math for that. You can copy this down and use this for yourself if you need this in the future. So for a V8, it's 4 times the RPM equals, and you put a line here, and then divided by 60. Gives you your frequency in hertz. Okay. Now, I know I'm going to get this question. What is this number 4? And what is this number 60? Well, the number 4 is the number of pulses per revolution. But in order to make this very easy on yourself, it's half the amount of cylinders. Okay, so if you have a V6, that's obviously going to be 3 times the RPM, right? And if you have a 4-cylinder, right, it's going to be 2 times the RPM. Everything else stays the same. Okay. And here we go. So in order to know what frequency we need to enter into our function generator, we need to figure out, what's going to happen at 3000 RPM, what kind of frequency we need. So in order to do that, I get my calculator out here. Hope you can see that okay. So turn this on. So 4 times 3000 divided by 60 equals 200 hertz. So if we wanted to fill this in, we could go 3000, and then hertz, we can go 200. So 200 hertz is what we need at our function generator to make this thing happen. Okay, and then for the V6, that'd be times 3 and all that, and we'll worry about that here in just a moment. Okay, and I'll also show you how to do the math to calculate the dwell angle. That's a little bit more complex, but we'll take a look at that here in a moment. So, and of course, that's assuming that this meter is even working at this point. You know as much as I do. It's just on the shelf here. Okay. So now what I'm going to do is put the function generator on the top here. So I'm going to take a look at that. And I have my leads over here. So I'll turn on the function generator and see where I'm at. Where am I at? Let's see, frequency. I'm a ways away from the mic, so pardon the low audio. So we need to set the frequency to 200 hertz. 200. Enter. Okay, the amplitude needs to be about 6.5. Yeah, 6.5 volts peak to peak. This is not terminated. The 50 ohm output of my function generator, which is this cable right here, is not terminated. So that's going to give me roughly about 13 volts, and that's what I need to drive this. All right. I'll explain more about that later on. If I terminate this into 50 ohms, it's going to drop the output a lot, and the function generator won't have enough output to actually drive this device because it's designed for a 12-volt vehicle, right? So that's a little trick there. A lot of people say, well, can you actually run the function generator without a load on the output? Well, in most cases you can. In this case, yeah, absolutely. So, of course, check with the specs of your function generator, but most are fine. Okay, symmetry, which is the pulse width, should be at 50% or close to. Let's see what it's at. Yeah, it's fine. Okay, and everything else should be okay. So we'll go back to frequency. All right. So now I'll connect the leads up, and what do you think? Drum roll, please. Okay. Let's see if we're going to get anywhere near 3000. So we should be center scale. Okay, so that's connected to there, and I will connect this up to here. And what do we get? About 2800. So not bad. It's off, right? To be expected. And this makes me question, I wonder what the scale linearity is like. So it's a little bit low. So let's test this at 1000. Okay. So we'll get the calculator out here. It's actually pretty simple. 4 times 1000, 4000. We'll divide that by 60. All right, so here we'll just go. I'll show you the process again. So 4 times 1000 divided by 60 equals 66.66 hertz is what we need to make this point at 1000. So let's see how good this is down here. So I'll go 66.66 entree. And we're not bad. That's not too bad. Looking at it straight on, it's just a touch below the line. And it looks pretty much the same at your angle as well. So it's a little more accurate on the low end of the scale. So let's try at 5500 RPM. Okay, right up here and see what that is. And this will really give us a good idea of the scale linearity of this device. Okay, so we'll go 4 times 5,500 RPM divided by 60 equals 366.66 hertz. Okay, so here we go. 366.66. That's right. And went up, bumped it up a little bit. That is way out. That's way off. So that should be up at this line here. So there is your perfect example of your scale linearity issues in a device like this. Now, if this was probably made by Sun or something like that, it would probably be spot on, right? You know, it hadn't been bumped around and trashed on too bad. But, you know, so we'll see what happens here, right? So we'll take a look at the insides and see if there's anything to calibrate that. I hope there's calibration controls. If there isn't, we're going to have to add them to make this thing calibrate. Okay, so let's go, let's say 8-cylinder low. Okay, so let's try 600. So I'll adjust this all up before I go switching the scale because it's just going to probably pin off the scale here. Okay, so we'll go 600. 4 times 600 RPM divided by 60 equals 40 hertz. Let's do that. 4, 0, enter. And we'll go low. Hey, that's almost spot on. Almost spot on. Okay, so let's try 1,000 down here. All right, I believe, if I remember correctly, I think that was 66.66. Let's try that again. Let's go 66.66. Enter. And as you can see, right, scale linearity, right? Let's try the 6-cylinder high, which is this one here, 6-cylinder high RPM range. Okay, so I'll click that up there. Now, the math is the same. It's just we change this right here. So instead of times 4, it's right times 3. So 3 times the RPM, it gives us our result. Oh, by the way, I think I neglected to mention what this 60 is right here. So it's very simple. 1 hertz is equal to 60 RPM, and there are 60 seconds in a minute. All right, so that's what that is right there. So number of pulses per revolution over here, or again, half the number of cylinders, and then that. All right. Okay, so let's do the math. So we want to be center scale here for 3,000 RPM. So what we're going to do is we're going to go 3 times 3,000 divided by 60 gives us 150 hertz. So we're going to have to put that into the function generator. So take a look at the function generator again here. 150, enter. And I will attach the clip back up again. So I'll attach the function generator to the meter here. And as you can see, it's down about the same. So you know what that really almost looks like? Either factory miscalibration or possibly something has aged. Maybe the meter itself has been damaged in some way, shape, or form. You know, these things, they usually see a pretty rough life, but it's very close. The other one is 2800, looks like at about 2850 or something, maybe close to 2900, right? Okay, so let's try the 6-cylinder low for 600 RPM. So let's go clear. 3 times 600 divided by 60 equals, so 30 hertz. Or 30 cycles, if you like. So 30, enter. And you can see, you know, a little bit far off on the upper one there, right? Usually when you're dealing with that type of scale, you're on the other scale. That's showing about just about 600. So I'll move this down here, and as you can see, it's actually pretty close. That's not too bad for the 6-cylinder low. So, and I wonder if the linearity is somewhat the same. So, again, we'll do this. 3 times 1,000 RPM divided by 60 equals 50. So let's see what it says at 1,000. 50. Enter. Not too bad, a little over, 1,000 there. And that's actually not too bad for that scale. So yeah, Interesting. We'll have to look inside and see what we come across. Undetermined there. So let's try 1100. Okay. So 3 times 11. Oops. 3 times 1100 divided by 60 equals, so it's 55. Let's go 55. Enter. Not bad. Not too bad for that scale at all. So it might be just decalibration. Who knows? We'll find out. Okay. Well, that's good enough for that. Let's take a look at the dwell next. Let's check that out, and then let's open this thing up and see what's inside. Let's test out the dwell function and see how well that works. Okay, so I'll move this over to dwell. So now we have a V8 setting here, and we have a 6-cylinder setting. You can see they're tied. There is no separation here between 8-cylinder and 6-cylinder. You know, there's no multiple positions, right? Again, the scales are tied together. And that all has to do with the ignition system in your vehicle. So anyways, I'll talk more about that here in just a little bit, more specifically the distributor. Okay, so you can see on the top we have dwell, and it says 45 degrees, and that's the maximum for the 8-cylinder setting. So that's very important for our math. So just say we have a 50% duty cycle set up, or symmetry is at 50%, like it would say on my WaveTech. So what we do is we go 50%, because that's where it's sitting right now, and I'll show you that, times, and it's 45 is the max, we go 0.45 equals, and that should give us 22.5 degrees. Since the bottom scale stops at 60, so that's for the 6-cylinder, if we go 50% times, because it's 60, it's 0.6, you see how that works, right? Equals 30 degrees. Now, if we look at the two scales, you can see we have 30 degrees, and if you follow that right above it, we're at 22.5. See that? So by varying the duty cycle, we can also vary the scale here. So say I want the upper scale to be at, say, 30 degrees. Okay, so I want the 8 cylinders to show 30 degrees and get very close by entering, say, 66.67%, but it's going to round me down to 66. So that would get us very close. So if I go, say, 66% times 0.45, right, I'm going to come very, very close on the V8 scale to 30 degrees. Okay, and that'd be right center, very close. It's actually, to really get that close, at 66.67, right? But so I'll show you what I mean here. So if we take a look at the function generator again, I'll just get this out of the way so I can put the function generator at the top and get this off of here. So function generator back up, and I'll hook up the leads again, and I'll go up there and I'll adjust some stuff and show you what's going on. So I'm at 55 hertz. It doesn't matter, 55, 60 hertz, whatever, for this test should be absolutely fine. That's still the same setting that we were using in the 6-cylinder position there. Now, if I go to symmetry, you can see I'm at 50% right now. So 50% should give me 22.5 or 30, right? Same thing. 30 is a nice little mark there, but you can see I'm above 30. So if we go 20, 21, 22, that would be 22.5 there. So I'm actually at about 23.5. Right? Again, 30 would be 22.5. So if I go up here and let's say test for 30 degrees up there on the 45 degree scale, right? I need to set it to 66. So I'll move the symmetry, or the pulse width, to 66. Okay, that should be close. And as you can see, it's a little high there as well. So 30 would be right in the center, right? So again, out of alignment just a little bit. And that looks relatively linear from that point to that point. Again, since I would be using this myself for V8s, it would you know, sit somewhere between probably 28 and 32, right? Is where this meter would be working for me, right? So dwell, or cam angle if you like. Sometimes it gets confusing when you look in the manuals. They'll say cam angle as a dwell. You can look at it like that as well. So what else can I tell you here about this before we open this thing up? I think that's pretty much all for this. So let's see if we can calibrate this thing. Let's open it up and see what it looks like inside. You know, I have no idea what's inside this thing. Hopefully it's not disappointing. Okay, let's take a look inside. See what's inside this thing. This is always exciting. So it looks like there's only 4 screws here. And they come out relatively easy, which usually indicates that it hasn't been part or cross-threaded. So it looks a little bit rusty. Huh. Okay. Probably been under the hood of a car when it's raining, working on a car or something like that at some time. Who knows? So, everything tells a story, you know. Open this up, antique dust on this thing, so goes out of the way. So what do you think's inside? Not a whole lot by the looks of it. Little circuit board down there. This looks like it's just probably going to slide out of the case. And it does. For building projects, these types of cases used to be very popular. Out of the way. Take a look at the back side. Actually looking pretty good. Why the wedge-shaped circuit board? That's kind of strange, isn't it? It's shaped in kind of a wedge. Why not just square? Well, we have an adjustment here. And 4 adjustments here. So that's 5 adjustments in total. How many positions are there in this? So that's off. 1, 2, 3, 4, and 5. Haha. I think we have an adjustment for each one. Look at that. 6H, 6L, so 6 high, 6 low. 8H, 8L, so 8 high, 8 low. And that would leave this as the dwell adjustment. Well, isn't that nice of them to mark that? Mind you, we could have traced that out pretty easy just by following the positions of the switch, but it's still nice of them to do that. Two electrolytic capacitors, which could get changed. They are so cheap, why not change them? So before I attempt to even do an alignment on this, I'm going to spray contact cleaner in all of these and move them around. And probably resolder this switch because the solder on that switch looks pretty bad. It looks like there wasn't very much solder when they put that together. Look at that. So resolder all of those. So a little bit to do here. So we can probably get rid of this. Grab a screwdriver here. Like so. That looks to be about 7/16 or 12. Probably 12. Yeah, most likely 12. Do I have 12 here? No, I don't, but I have these horribly spray-painted vice grips. No, I don't agree with this, but there's a washer behind it, so I can very carefully grab onto this without scoring anything. As you can see, there's space there. And let's give it a bit of a twist. Look at that. Precision. Precision with a very scary looking vice grip. Okay. Get that off of there. Look at that. Got to be careful with this, so I don't want to pull that out of the meter. Looks like it's ready to do that. What's the IC say? OKI. OKI Electric. It's been a while since I've seen one of those. MSM 4049. So that's a 4049. So basically like CD 4049. Same kind of idea. And if I remember correctly, I think that's a hex inverter. So anyways, very simple design. Very, very, very simple design. Get rid of this because it ended up falling off. Okay, so what I'm going to do is get the soldering iron heated up and get this desoldered, and that way I can put this off to the side so I'm not tugging on these wires. I'm very leery about pulling those out of the meter. Should actually put a little spot of glue on here or something like that just to be careful. And I'll start cleaning things up and resoldering things, and then we'll start doing an alignment. Just before I remove the meter, I added a bit of super glue right to these leads. So these are super glued directly to the back side of the meter, and also put just a touch under this tape that was coming off to keep the dust out of the meter. So that worked very well, so I don't have to worry about pulling these wires out of the meter anymore. The meter is in, very nice condition. It does have a little scratch on it that it's received somewhere along the lines, but other than that, it's pretty good. As long as there's no really bright light directly on it, it's pretty good. So I resoldered the entire switch here, and that's how it should look, not like it was. So whenever you're dealing with something that's going to have any type of movement or could have any type of movement, there should always be lots of solder on the contacts. So if you ever take any type of switch apart or anything like that, it's always the things that you inspect first, anything that really gets the mileage, I guess you could say. I replaced one of the capacitors here already, and this is the one here that came out. So this is the one that I had, 220 at 35. Very good quality capacitors. And this one here still needs to be done, so let's do that. So let's grab this here. And that comes out of the board there. Get rid of that. Take this out of there. 10 volts, 47. Have a much nicer capacitor here. Put it down like so. Hopefully that'll stay. No, it won't. Of course, because the solder roll is going to move it. Okay, stay. There we go. And there it is. In order to clean the switches in here, basically all I do is just give it a shot of contact cleaner and move it around a whole lot. Like so. And then just do this. And after you've done that, you want to make sure that you hit each end, right? So that you go through each contact and then rinse it off. Because what this is doing actually right now is this is removing the debris off the contacts. So you do this too much, and then of course you're just smearing the debris around. So give it a good blast every now and then and just wipe the debris off. And that should be good. And then of course now I need to do the VRs. So if it wasn't decalibrated then, it will be decalibrated now. So let's put this in here and move this around like so a little bit. If you don't do this before you do an adjustment, a lot of the times you'll get a very jumpy response. So I'll put them roughly back to where they were. They're all going to get realigned anyways, Right there. Kind of just go one at a time. Very needed step. Again, if you don't do this kind of stuff and you try to align it, you're setting yourself up for some issues. There it is. So I'll dry this all up. And I'll get this put back into the case, all back together. And we'll do the alignment. I think you can do that by possibly just slipping this back up just a little bit from the case. I'll show you what I mean here in just a moment. So I'll get this all cleaned up and dried up and ready to go. Many of these meters come from the factory aligned at the top end of the scale for the tachometer settings. And then for the dwell, it's a little bit different. I'll talk about that when we get to that point. So I have the selector switch for this meter right now on the 8-cylinder high RPM, and we're going to align the up to 6,000 RPM scale. So the first thing I want to do again is make sure that the needle is sitting on the 0 mechanically, and it is, so I don't have to worry about that because we adjusted that earlier, right? So what I'll do now is I'll go 4 times 6,000 RPM divided by 60 equals 400 cycles. Now, in order to save some time here, I've already entered that into the function generator. So if you take a look at the function generator, you'll see that there. What I'm going to do is attach the tack to the function generator right now, and we'll see where those VRs ended off. So we can see that VR is out of adjustment. Remember, I cleaned them and moved them just to random spots. So what I'll do here is I'll slide that to the back. I'm just going to take this off camera for a second because I've got to poke this in the back here and see what I'm doing. And I'll get this up here and move that back. Like so. And that looks like that's right on top of the 6,000, doesn't it? Perfect. Okay, so I'll put this back down. Now let's see how well this tracks. So what do you think? So let's try 3,000 RPM. So that should be about 200 cycles, correct? So 4 times 3,000 divided by 60 equals 200 cycles. Okay, so I'll set the function generator up to 200 hertz. 200, enter. Oh, look at that, how close that is now. And that's pretty decent. So now, what we'll do is we'll test this at 1,000, and if it's right on 1,000, then we definitely won't be touching anything. So that's very close. It's right at the edge of that bar. It's like, how much closer do we really need to get with this analog scale, right? So let's go 4 times 1,000 divided by 60. 66.66. So I'll adjust this up. 66.66. Enter. Look at that. Does it get any closer? That is very good. I'm definitely happy with that. Okay, so 8-cylinder high RPM adjusted and successful, very successful. So now I'll set everything up for the 8-cylinder low RPM adjustment. Let's align the 8-cylinder low RPM setting. So that is the second scale down here, just below the yellow bar. So we want to align that right at 1,200 RPM as well. So let's do the math here again. So we're going to go 4 times 1,200 divided by 60 equals 80 cycles or 80 hertz. So if you take a look at the function generator, I have that already set up to save some time. And I'll attach this to the meter with the clip here again, and we'll see where we're at. And we're over the top again. So what I'll do is I'll take this off of here, and I'm just going to turn this around and fit this in the back very carefully so that I don't damage anything. Okay, and I need to take that back down to 1,200. So let's see, get this really close up here so we can both see this. Make sure I go the right way. It's very touchy. It's looking like it's right on top of it there, isn't it? Okay. So we're doing pretty good at this point. So far with the upper scale, as that's on top. Well, it's a little bit high. I think I could do a bit better than that. Let's see here. I'll put this back in. And I am just breathing on this. Okay, that's very close. Okay, so I'll put this down here. Hey, the accuracy is only as good as the alignment, right? Okay, so now, go clear. So we're going to go 4 times 600 divided by 60 equals 40 hertz. So that'll be right at 600 RPM there. Okay, so we'll go 40, enter. Look at that. Does that get any more accurate than that? Really? That's just spot on. So now the truth. We're going to be some pretty low frequencies here. So let's try it at 200 RPM. Okay, so we'll go 4 times 200 divided by 60 equals 13.3. That's some pretty low frequency. Okay, let's try that out. 13 point, what is it? 33. 33. Enter. Oh, that's right on. And the frequency is so low that it's having a hard time filtering that. That's that 220 microfarad capacitor in there that's smoothing things up, right? So at 13 hertz, you can see the jiggle of the needle. That's kind of neat. It's right at 200. Doesn't get any more accurate than that. So far, so good. This is turning out to be a very nice meter, actually. So I have a feeling that probably somebody got in there over time and screwdrivered it. Okay, so on to the 6-cylinder high setting. Let's set up the 6-cylinder high RPM setting. So we need to align that again at 6,000 RPM. So we're going to go 3 times 6,000 divided by 60 equals 300 cycles or 300 hertz. So take a look at the function generator. You'll see I have that there already. I'll attach the lead up again, the signal lead. And this is actually pretty close in this one. Let's see how close that is. Just a little bit low. So I'll pop this in there and align it up. As close as we can here. Okay, that's very close. Okay. So there we have it. Right on top. So, we'll clear. 3 times 3,000 divided by 60 equals 150, which would make sense. Half of 300. 150, enter. Look at that. That's right on top of that. No problems there. And we'll try it at 1,000 RPM. So 3 times 1,000 divided by 60 equals 50 cycles. 50, enter. Look at that. Right on top of the 1,000. Okay. So that's successful. Now on to the 6-cylinder low. Let's align the 6-cylinder low RPM scale. So that's up to 1,200 RPM here, right below the yellow line. So 3 times 1,200 divided by 60 equals 60 cycles or 60 hertz. We take a look at the function generator. So what I'll do now is I will attach the signal lead, and whoa, it's right off the end there. So I'll adjust that up. See how accurate we can make this. Okay, there we go. Very touchy. Oh, I think I'm right on top of it right now. There it is. Right on top. Okay. Very touchy. You just look at that screwdriver and that's changing. So I'll move this out of the way so this will sit somewhat normal. Okay, so if we want to go half scale, that's going to be half the frequency, 30 hertz, just to make things simple. Let's go 30 hertz. And look at that. That is accurate, right on top of that 6. So at 6 cylinders and at 200 RPM, that's going to be a very low frequency. I guess we're going to see some pretty good needle jitter with this one. So for the fun of it, let's try that out. So let's go 3 times 200 RPM divided by 60 equals 10 hertz. And we're going to see some good needle jitter there. 10 hertz. There we go. Look at that. Right on top of 200. Perfect. It's almost like it's cleaning the little tube. So that's perfect. So all the scales line up very well on this. Again, I'm actually impressed with this little thing. All right, so let's see if the dwell will hold up as well. We'll do that next. Let's align the dwell. So in order to get to a solid number like 30, which means 22.5 on the V8 scale, so 30 is on the 6-cylinder scale, it's 50 times 0.6. Okay, so if you recall earlier the math that I showed you, so it's 50 times 0.6 equals 30. Okay, so that should give us 30 degrees. So if we take a look at the function generator, I have the symmetry at 50 up here, and I've moved the frequency around as well, so it's back up at 60 cycles, I believe. Yep, it's back up at 60 cycles. So all I need to do now is attach the lead here, and let's see how far off we are. And it's a little ways off, so I'll just move this out of the way, and I will adjust this right to 30. That's a solid number. So get this closer to the camera here. Right there. Okay, right on top of the 30, or 22.5. All right, move this out of the way. So let's see how accurate this is. So if I want to see 50.4, because with the percentage, with the symmetry, I can't go point something. So it's either 50, 51, 52, 53. So I can't go 51.5 or anything like that. It has to be, this is the reason that I'm aligning it at the 30 mark. So if I want to see if it's aligning up here, I can get to 50.4 by giving it about 84% symmetry here. So I'll go clear, go 84 times 0.6 equals 50.4. So it should just be over the 50 line there. Okay, so let's enter 84 into here. 84, enter. Look at that. It's just over the 50 line. Right, so almost 50 and a half right there. You see that? Very, very accurate. Even in the dwell setting, it's just surprisingly accurate for an analog meter. And let's try this. So if we go clear, we go say 34, I believe it was 34 times 0.45 equals 15.3. So we'd be just above the 15 line there. Okay, so I'll give it 34%. 34%. And look at that, right above the 15. Just a touch above. So the dwell is spot on as well. So all I have to say, it's completely aligned and project successful. I honestly have to say, I was very skeptical of this Sears professional dwell tack, but after it was aligned, cleaned up and a few components changed, this thing is phenomenally accurate. It really is. So if you have a chance to pick one of these things up and you are working on a car, well, you've seen the accuracy yourself. So after an alignment, it's, just very, very accurate. I wasn't expecting anything like that from this little device. So I imagine most of them are probably like this. I can't see very much variation in the circuit. It's so incredibly simple. So if you work on older cars or, whatever you need a professional dwell tack for, this little device works. Now, this won't work for a 6-volt car system. This is designed around a 12-volt system. I'm going to design a circuit that will adapt 12-volt, dwell tack meters to a 6-volt system. And I will share that as well. Hope you enjoyed. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. If you'd like to be notified as soon as I post a new video, don't forget to tap that bell symbol. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal electronic inventions and designs, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.